Can you make it full screen, please?
Yeah, you can see it now, right?
Yeah, I can see it now. Absolutely.
Okay, now
Okay,
it's
perfect. Perfect.
just 1 second.
Yes.
Sorry, once more. I'm sorry.
Are we ready?
Okay. Yeah.
Yeah.
So can we start?
Yes, absolutely. So it's a pleasure to introduce Professor Boris Gutkin, who is currently at the Holon Institute of Technology in Israel. Um, Professor Professor Gutkin did his PhD at the Weizmann, and after his PhD, he moved off to a postdoc at Sakle, and then he moved to Germany, where before this position he was a long-term he held a long-term position at the University of Duisburg Essen. He also holds a visiting professorship at Georgia. So in the interest of time, I will not stand between you and Professor Gutkin. So Professor Gutkin, the floor is all yours.
Okay, thank you very much for introduction, and even more for invitation to give a talk here. We'll talk about very simple model, and basically coming back to Thomas Prosen's talk from yesterday. So he told us that dual unitary models can be looked as kind of cat maps of the many-body quantum chaos, and I will take it very literally. In my talk, I will just consider cat maps. Yeah, so I take it this message very straightforwardly. So okay, so what I will tell you, so it's basically how one can generalize the standard model of quantum chaos, so Arnold's cat map, to many-body setting. And there are certain things which should be emphasized probably. So one nice thing which we have in single particle quantum chaos and often lose in many body setting is that we have a semi-classical toolbox. For example, we can use some information on classical side, like periodic orbit correlation, to extract out of this something on the quantum side. For example, correlation between eigenvalues of the system. And this is often lost in many body setting because people try to keep dimension of Hilbert space as low as possible, and this has its own price. So for models like SYK, we don't have something like semi-classical limit, or more precisely underlying classical system. Yeah, here I'm going to talk about models where we can actually keep our classical dynamics. And in addition, as we will see, so these models have this nice feature of being dual unitary. So we can extract something also on this side. And moreover, so you will see that they're actually quite special, even in this restricted class of dual unitary model. So they're quite special. One another thing which I want to emphasize from the start, I will consider not just cat maps, so I didn't point it out here, but perturbed cat maps. So and this is very important if you want to kill some non-generic features of related to linear dynamics of these models. Okay, so let me start from single cat map. So one thing which I want to emphasize is that we can look from two perspectives for so it's standard one is we look in the coordinate momentum space. Yeah, so this is usual Hamiltonian dynamics. So we have a linear map. I didn't add here perturbation, but in principle we can add a perturbation here. And we have a pair of winding numbers which restrict our coordinate and momentum to unit interval. So, but there is another way to look at this model. So if you just consider it rid of the momentum, so then you can bring it to the Newton form or Lagrangian form, and this is very much like standard Newton equation in the discretized setting. So you have some kind of second derivative, discrete second derivative here, linear, and on the right side, so you have linear force, and then in addition you can add some arbitrary potential if you want to break up this linearity, and very important, so you need these integer numbers, which I denote here MT, so this is winding numbers, which restrict your dynamic to circle, basically. Okay, this is standard single cat map. So now let's see how we can build up out of it something many body. And the idea was straightforward. So we tried this in 2016 first time. So and the idea was that maybe we want to first to keep these linear features of the model. So you just take a bunch of cat maps and couple them linearly with linear interaction. So here's a part of action which describes this linear interaction. So and nothing kind of, so this is a natural idea, and you can keep your perturbation if you wish, and then you generate some dynamical equation. And you can see it also, so like in single cat map. So you can also see, look at this in the coordinate representations as just your particles are bounded to a circle. Yeah, so you can think about cat maps as kind of particles. Yeah. So was the question? Or? Okay, now because coupling is linear, so you can actually think about everything here as a one big cat map, just defined in a large phase space. Yeah, and if you and because if you don't think about the perturbation, so the model is quite simple. Because of this nearest neighboring interaction, so we only couple nearest neighbors. So it's sufficiently simple to analyze dynamics on classical side. For example, you can calculate all Lyapunov exponents in this case and see when your model is chaotic. And the condition here is slightly more stricter than in a single particle case. So use this A plus B. So this is parameters which define dynamics of single cat. It should be in single cat, so it should be larger than 2. So here it should be larger than 4. But if it's larger than 4, then you guarantee that your dynamics are fully chaotic, and you also can expect ergodicity in this sense, so that you have a unique invariant physical measure here. So this is very nice. So and then you know by general kind of considerations that perturbation, if it's not too strong, usually doesn't break up this separability. So many things actually in classical chaos are stable under perturbation. One nice thing is that I told you that single particle case. So when you rid of momentum, so you can bring in the standard Newton form. So the same thing you can do here. So the only difference you see, so you get a very similar equation like for a single cat map. But instead of just second derivative here, so here you have a discrete Laplacian. Yeah, so because you have now two coordinates, so one is so one of them is just a position of this cat, and another one is time. Both are discrete and they're in the sense on the same level. So you can see this equation actually. So there are so you can see as kind of discretized field theory. Yeah, so which is defined on lattice. Now, one important thing here, so already on this level, so you can see some kind of symmetry and the exchange of coordinate and position of these particles, of these cats. So you can use this equation actually to also in a different sense. So you can use this winding numbers, which restrict your dynamics to unit circles. You can now use also as kind of symbolic dynamics. And it turns out that it has actually very nice properties. So you can uniquely encode, for example, your trajectories by this set of integer numbers. And you also know how to connect, because of linearity of these dynamics, you also know how to connect, at least in the non-perturbed case. So you also know how to connect your symbolic representation with actual coordinate momentum representation. So you can go easily from first to second and the opposite way around. So which allows you, for example, have a very good control on periodic orbits in the system. So you know how to encode them, at least. And this symbolic dynamics actually has some other nice properties. So I don't go to the details. We wrote some works with I wrote some works in collaboration with Frederick Cvetanovic about this. So you can, if somebody interested, I can give references. But this is not the main point of my talk now. So I want to emphasize this space-time symmetry. Or so what I told you. So we have explicitly symmetry of the system under exchange of coordinate and time. And this is a classical analog of this dual unitarity, which was mentioned in almost every talk here. So, but now it's on the classical level. So you can extract out of this several things you can see immediately. For example, because of this symmetry, you see a conjugation between periodic orbits. So what means conjugation? It means that if I have some n-particle periodic orbits of period t, there is a corresponding t-particle periodic orbits of period n. So if I take just exchange times and spatial dimensions here. And moreover, so these periodic orbits, so they are related one-to-one, but it's also their actions are equal and their stabilities are equal. And you can, using this, you can start to extract some fancy mathematical identities, which are based on the fact that the number of orbits in n-particle case should be the same as the number of orbits of t-particle case if you exchange also the periods. So this is just kind of a side remark. This is probably the shortest way to get something like this identities, which are actually something known in the mathematical literature, but here you get it in one line if you just use this duality. Just a kind of curious fact. So now this is on the classical side, but it has immediate, you can immediately suspect that there is something also on the quantum side. And the reason is that if we use semi-classical trace formula, yeah, which it should be for a cat maps, actually something for a non-perturbed cat maps, it's something exact. So you can relate it to, you can expand trace of evolution operators in terms of periodic orbits. And because of this duality on the classical side, you can argue that so because stabilities and actions of this periodic orbit should be conjugated, so there also should be equality between these traces. Okay, this works in a precise way for a non-perturbed cat maps because the trace formula is exact. For a perturbed case, you could still wonder whether this is exact or just semi-classical approximation, whether I should keep equality. But it turns out that it's actually exact. And the way to see it is to split actually dynamics into two steps. So you can do it. So we usually think about cat maps as a single map, but you can split it in actually in two steps. At the first, you just kick each cat individually, and then on the second step you couple them. Yeah. So if you do this like this, so then it's not difficult to see that the quantum evolution it can be split in the same way. So this interaction part and tick part, and this leads to actually to a way to represent traces of evolution operator as some kind of partition function. So if you write down your traces evolution operators in you insert at each point time your unitary resolution, and then you can write down this these such traces as part in the form of partition function. And here again, so you see that everything is symmetric under the n and space and time exchange, which means automatically that such trace of unitary operators in the power of t of cat map evolution of cat map in the power of t, I can conjugate so to trace of evolution of t particle cat map in the power of n. So I get this quantum realization of space-time duality in quantum setting. So, and this is quite natural. So when we think about this, because this partition function, so we know from the statistical mechanics, yeah, so that the time evolution here basically it's evolution of system in the time direction, and what is here, so it is the space evolution. So it is evolution in the space direction, the second direction. And we know that also in statistical mechanics we can always represent for a two-dimensional system, we can always represent partition function in two different ways. One is through the transfer operator in the first direction, and and another way to represent the same partition function is through the transfer operator in the second direction. So here it's exactly the same story, just we have a time direction and we have a space direction and evolution in both of them. So it turns out in this particular class of models, so it turns out to be exactly the same evolution. In general case, so it could be that one of them is time evolution, namely time evolution must be unitary, but the second one, in general case, it's not. But here it turns out that this is exactly the same unitary evolution. This is exactly the dual unitarity, which the main subject of this conference. Okay, so this is what we see on the level of traces. We can actually take this information and translate it to the spectral form factor, and at least for a short times. So this might be used to extract information on the behavior of system for a short time. So what I do here, so I take a trace of standard form factor, which is trace of unitary evolution in the power of t, squared, and take average, let's say, over some potential, some perturbation potential. So you can think about this as kind of your averaging parameter. And then immediately by this dual unitarity, so you can relate it to the evolution basically of the same operator, but for t particles, but now in the power of n. So now if t is small, yeah, so let's say finite, so we actually back to our standard quantum single particle setting, because you can see about t as kind of number of particles. If it's small, so it's nothing more than a single or in quarter mark single particle quantum chaos. And from there we can arrive to conclusions that actually, because we know that cat map is fully chaotic system, so everything here should be described by form factor of random matrix of the corresponding ensemble of random matrices. And for a short time, so it gives you initial information on the behavior of this form factor. And in particular, you see kind of strange thing for a very short times. Yeah, so you can see this form factor should go to 1, and this from this you get immediately that you get exponential growth of form factor for a very short times. But this this duality is actually useful for a short times, yeah, because we can extract by this dual transformation we can relate things to our normal single particle quantum chaos, which we used to think that we know what happens there. Okay, so for the larger time, the situation is more complicated because you basically need to think differently. Because if in single particle chaos, your trajectories are kind of one-dimensional creatures, so something like this, what is on the right-hand side. So we know more or less how these creatures are correlated after the famous work of Sieber and Richter. So we do have understanding how the correlation between periodic orbits happen here. So for a system which I'm talking about, is many dimensional. So if your spatial dimension is really both spatial dimension and time dimension are really large, so you must think about them as kind of field theories and discretized field theories. And this means so that your trajectories are not anymore some kind of single dimensional trajectories, but rather like something like two-dimensional surfaces. And you need to actually to completely review all your semi-classical toolbox and ask whether there is in this among these two-dimensional surfaces which represent your periodic orbits, so there could be something like Sieber-Richter pairs of correlating partners, which lead us to the RMT result. And this program was kind of the only thing we were able to right now to prove rigorously this existence of such two-dimensional Sieber-Richter pairs. And so this can be done on the level of symbolic dynamics. So you can build these Sieber-Richter pairs by using your symbolic dynamics and then translate it back to the phase space. So what you see is here, so it's two different periodic trajectories which have some kind of, so they have a common structure in the sense that this so this black part of the coding, so it's coincide, and blue part is also so this is so-called encounter region. And the only difference is that we exchange this green and red parts. And this is something reminiscent of usual Sieber-Richter, how you build Sieber-Richter pairs in single particle systems. But so and here you can go back in the phase space and show that these are really two trajectories. You generate in this way two trajectories which are very close to each other, but they are different in the sense that they go in a different spatial time order through the phase space. Okay, so this is but the actions are very close, and this means so this is exactly the kind of analog of Sieber-Richter pairs, and this one contributing to the spectral correlations as well.
Boris, if I may make a small clarification because I'm confused.
Yeah.
About these surfaces. I mean, in any dimension, a periodic orbit in a fully chaotic system will be isolated. So what exactly are these surfaces?
Surfaces here supposed to represent periodic orbits, or more correctly, so one should call them periodic theory. So if think about field theory. Yeah, if you think so, this is, of course, this is something. If you think about system, many body system, so you have two parameters. Yeah, so now, so you have time, but you also have a space. So, and if you want to represent your trajectory somewhere, something like in phase space, so these are two-dimensional surfaces. Yeah, so this is kind of caricature for this. Of course, this is not. This is not.
These are not the orbits in the large phase space. They are
exactly. So you don't think about as kind of single particle in the huge phase space. Rather, you think about kind of two-dimensional surfaces in the relatively in the space-time. Yeah.
Okay.
In some kind of configuration space. Yeah, as a momentum or just coordinate. And you can, the symbolic dynamics helps here very much because you can actually make a rigorous picture out of this. Yeah, so if you go to the level of symbolic dynamics, so you again, so the same story. So instead of kind of in single particle systems, it's, when you want to represent your trajectory in some kind of symbolic dynamic representation, so you get array of symbols. Yeah, so sorry, string of symbols, just something one-dimensional. Here you encode your dynamics by 2D surfaces. So one of this dimension is space, and another one is time. And in this way, you can make things very rigorous. Yeah. So this is actually this is two actual trajectories. Yeah. So you can just check the existence, how close they come, and what is the action difference. So everything is under control. The only problem here is to estimate this statistically. Yeah. So you can easily build up these things individually, but the problem is to quantitatively estimate the contribution in something like spectral form factor. Yeah, so this is still a very big challenge.
Thanks.
Okay, okay. Now I go to something different. So I just want to talk maybe to go to mainstream, to more kind of mainstream problems, and to short about dynamical features of this model. So because they are dual unitary, so there are a huge number of works in recent years dedicated to these dual unitary models. I will talk about something very special corner of this. So I will talk about correlators. And so that one amazing feature of this model, so that in many senses they are amenable to exact analytical treatment. Yeah, so they're kind of solvable models in quatermass. Not everything here is solvable, of course, but certain questions are kind of. It turned out surprisingly that you can calculate certain things quite exactly, quite precisely. So, and one of them is the correlator. And here, I just want to give you a general picture, so general kind of argument why you can calculate correlators here. And the reason is that, okay, so it's a mixture of causality and duality arguments. So if you take two observables, which are kind of separated far away from each other in space, or something like on my picture here. Yeah, so the signal propagation here is 1 in this model, so to say. And if you observables are separated too far away in the space, so it's clear so that they are uncorrelated. Yeah, so the correlator between this Q1 and Q2 is just 0 because they are outside of this cone line. But then something strange happens because of this duality. So you can argue, okay, so if I take Q2 not on this spatial part, but on by symmetry, I take it here. So by duality, by this spatial time duality, so the correlator should be equal. So I come immediately to conclusion that there should be 0 also here. And this means so the only place where they can be non-trivial, so this along this blue line, this cone light borders. Yeah, so to say. So only on the borders, so they can be something non-trivial. So this is of course something very special. What is even what turns out is that not only this, but on these borders you can calculate them precisely. And this is, of course, very special for these dual unitary models. So, and cat map is one of them. So you can use these ideas and write down your correlators in terms of, first of all, you write down standard definition of your correlator. So it's evolved. So it's some kind of local operator. The sigma 0, it's a local operator. So it's operator which is localized on two sides. So it's, I look here for operators which are localized on two sides, not on one side, and which is and then I correlate it with another operator which is located somewhere in the different space point n. And by this duality argument, so we know that the non-trivial correlations, they come only when n is equal to t. And so along this Lycon borders. And moreover, so we can write down this very generally. This is something very general for this dual unitary models. So you can write down them in terms of transfer operators. So some kind of low dimensional transfer operator. So the dimension of this operator is like dimension of your Hilbert's local Hilbert space. It doesn't depend on the size of your whole system. So it's just not there. So it is just the dimension of local Hilbert space, which defines the dimension of this transfer operator. What is special? So this is yet very general for dual unitary models. What is special for cat maps, for perturbed cat maps, that you can actually very precisely to calculate the spectrum of this transfer operator. So which means that you can explicitly calculate your correlators. So not just to give them in terms of some known transfer operators, but also to calculate the eigenvalues of this transfer operator, which defines your exponential decays of your correlator. So here is explicit formula what you get for a cat map as eigenvalues for this transfer operator, and this I emphasize this. So it's for a perturbed cat map. Yeah, so it's you can. If your perturbation here is 0, so the spectrum is very peculiar. So it consists only of one or two or several. So I don't remember exactly now, but eigenvalues which are 1, and the rest is 0. So you come to conclusions that generically, so as expected, yeah. So your correlators decay exponentially, but there are some kind of exceptional cases and exceptional observables which you can construct. So there could be artificially constructed some observables which are actually don't decay for some choices of potential. Okay, now you can actually ask. So this is in quantum setting. It's actually quite interesting that you can extract classical results of this for a classical correlator. So just take in this formula, so you take a limit when the dimension of Hilbert space goes to infinity. So extract your classical result very precisely. So this is kind of might be surprising because for a single cat map, so you can try to get correlators for a single cat map, and it is you cannot get them at least in such explicit form. Yeah, so you can probably get a lot of kind of nice bounds and nice statements, but for a single cat, but not something so explicit like here. So it shows you that in a certain sense, this many body cat maps are actually simple in a very strict sense. So it's simple, simpler than single particle cat map. One should add, of course, in the thermodynamical limit. Yeah, so if I don't take thermodynamical limit, so this is only in kind of when the system is so these results are valid when the size of system is sufficiently large. Okay, now one additional comment is that if potential is 0, so you have a strictly linear case. So this is what I told you already. So on the classical level, you get something strange. So you get that all your exponents except of 1, they're equal to 0. So which means that you basically have your correlators are trivial in a sense that they are, so your local observables are non-correlated. But here one should add, so the important thing is here that is local. It means that you consider times which you consider here should be larger than support of these operators. So if times are shorter than support of this operator, then you do still you do have some correlations. But if times becomes larger, so so the model actually is kind of strangely so uncorrelated in a sense, yeah. So that your correlators not just decay, so they basically vanish if you take a large time propagation. So large in the sense larger than support of this operator. So all your correlations are in a sense are ultra local, so to say. And now one can take this what I told you so was valid for an arbitrary cat map model. So this, which means for a quantization with arbitrary dimension of this Hilbert space, we can take different dimension of the Hilbert space, on-site Hilbert space, and you can go to extreme non-classical limit when dimension is as low as possible, so L equal 2. So, and here you basically you realize that actually the model which you get in this case, so it's just nothing more than kick spin one half chain, yeah. So this is the same model which many people talk about. So when you have Hamiltonian is just a spin chain, so you connect your interaction are in z direction, so and you kick system in x direction, so to say. So this is a very basic model on this many body market, and now you can see that you can also, so this is a kick setting, yeah, so that you also split here in the interaction and kick part, and you can see it as just a lowest possible realization, quantum realization of cat maps, yeah. So, and here of course you have this duality, so, and the dynamics is in general, so it's dynamics are chaotic. There are, however, several integrable points. One of them are quite obvious. So this is for this 0 and pi half parameters, but there is also some kind of more mysterious point, which is classic. So which is classic. So it's not so clear. But on the spectrum, on the level of spectrum, you do see Poissonian statistic for these parameters. And it's not clear why it happens for this particular point. At least I didn't see an explanation for this. But except of these 3 points, so you do get spectral statistics, which is corresponding to random matrix theory. And regarding your correlators, so here you can calculate everything explicitly for any combination of observables. So you can get very explicit formula. So you can see that decaying exponents are given by this cosinus to h. H is this parameter which describes which sits in the model. And you see that for 2 integrable points, so this is exactly where this parameter is equal to 1, so meaning that there is no decay of correlations. But in any other point, including this mysterious integrable point, so you do have decay of correlations, exponential as could be expected. Now, what is more, so you can actually calculate. I talked about dual unitary settings, but in these models you can easily break up these settings by just changing the value of this j parameter, going from p over 4 to something else, and then the situation is of course changing in a sense that the correlators here in this case, so they are zeros, still zeros by causality arguments, so they are zeros in this yellow part, but in the blue part they are non-trivial. So what you can still do, so you can calculate them along this border, so of this con light. So your borders, you can still calculate these correlators, but not so you get explicit expression. But when you go inside of this cone, so the problem becomes difficult because your transfer operator, dimension of the transfer operator also grows. so this is basically the only place where you can calculate this is along edge borders, along borders of light cones. Okay, so now I come to summary. So what we learned from this maybe is the following regarding the spectrum of the system. So the situation is the following. So we basically, assuming that we know everything about single particle cat map, so we know two domains in this picture. So this picture represents, so somehow this is time and this is spatial extension of these maps. Yeah. So how many cat maps I take? So you know two corners of this models or understand. So the first one is the single particle quantum chaos. When you take a very short, let's say, chain and propagate for a long time. So we know that we basically have to get, for a perturbed case, we have to get to random matrix theory results. So this is well-established fact. So, but then by duality arguments, we know also this part of these diagrams. So when they actually something dual to this. So when we have a very long chains, but very short times, but duality arguments, so I can just reverse this time and space dimension and again get all my results just by coming to random matrix theory. Yeah. So what we don't know, so this is large part of this diagram where both times and spatial extension of spatial dimension of system are both are large. So here we need a genuine two-dimensional, so to say, many particle quantum chaos theory, in a sense that we need to take in account contribution between this 2D periodic orbits, and this we don't know.
Excuse me. So you have 2 more minutes left.
Yeah, so I'm finishing now. So I think it's kind of. So what I told you about, okay, so and this is of course a reflection of the spatial propagation duality between spatial propagation and time propagation, which is on the classical level. So it's expressed through this duality between periodic orbits, and on a quantum level. So this comes as a conjugation, so equality between traces of unitary evolution in time direction and space direction. Yeah, so here you just have equality between these operators, but general models of this type, so you don't have. So one of them is of these operators, namely the spatial propagation becomes non-unitary, so which is also kind of interesting, but but it's a different story. Okay, and in this sense, so perturbed coupled cat maps provide a very nice example of self-dual models with classical limit. Yeah, so one of the advantages here is that we don't lose our classical dynamics. So somewhere on the background, so we can also use this semi-classical toolbox maybe to investigate this model. And the spin 1/2 chain, this represents the minimal realization of this model. And models are exactly solvable in a sense, at least of in the narrow sense of these correlators, because local correlators can be actually calculated precisely, or so to say, represented in terms of some transfer operators. And in the case of cat maps, so we even know how to calculate the spectral data of these transfer operators. So this is the difference between kind of general models and specifically cat maps. So, and of course there could be all kinds of extensions of this research. So one could ask what is about this out of time of order correlators, disordered cases, and more general models, so you can go to larger dimensions and so on. So so part of these things we already kind of investigated, but part of the questions are still open. Okay, so thank you very much. So
Thank you so much. If there are any questions, you can ask now.
Yeah, Raj, maybe I can.
Yes, please, Arul. Yeah.
Thanks, Boris. Very interesting talk. So my first my first question, maybe it's an observation, is that your coupled cat map is not in the family of the kind of brick wall unitary circuits, correct?
You can, so what I know is that you can translate as this circuit setting, yeah. So circuit lattices setting, yeah, and then I actually I never looked at the in details what you actually get there, yeah. So what kind of gates you get there, but you can translate it, yeah. You can translate it
because we in thanks for citing our work. We had in that a brick wall structure of the usual kind, where there were cat maps at these as the two particle unitaries, and there were cases where there were two unitary cat maps, especially for odd local dimensions, and in that case, the correlations decayed instantaneously, like what you were talking about, the trivial. In fact,
I think it might correspond to this non-perturbed case.
Yes, yes, it is in the non-perturbed. We didn't include the perturbed case. So, but there was a difference between local dimension being odd and even. In your case, there is no such difference.
Not that
it's valid for all L.
I don't see where it enters at least. Yeah. So what is usually makes difference is whether times are odd or even. So this makes some differences. But
okay,
when you consider correlators, but I'm not aware. Okay, so not that I'm.
Okay.
I'm
So anyway, that's a minor point. But the thing is that the correlators of single particle or two particle support decorrelated instantaneously. So that was the correspondence to the classical Bernoulli property. So you have something very similar, but you have to wait for a time which is still the local dimension, I guess. Correct?
I think you still need to wait for times which are larger than support of these operators.
Support of the operator. No, but in that case, not. Well, yeah, I think in that case, well, yeah, maybe you're right. Maybe that's still, you have to wait for the two times. But could one extend this beyond two particle support?
Okay.
Because I was also discussing.
So at least I will tell you, for operators with support. Okay. So you mean what happens for operators with larger support? Yeah.
Yeah. Yeah.
On the classical level, I think you can be still sure that these correlators. So if you go just to classical models, yeah. So you have this option with cat maps. Consider just classical correlators. So you do, I think you still keep this property for operators with larger support. Yeah, so it's some kind of general statement for a non-perturbed, but this is true only for a non-perturbed case. Yeah, so we are talking about non-perturbed case. This. I think this is true for at least on the classical level. On the quantum level, I actually I'm not sure completely about this. So, but something, I guess there's something still something special. What can be also done on the classical level, in general case, we were able to calculate for operators with 3-point support, we were able to calculate things exactly.
I see.
Even with perturbation. Okay, so but it's only works for a 3-point support.
Okay.
If you take larger support, so then I just don't know what happens with it if you include perturbation. So probably it stops to be exactly solvable in this sense, yeah. So that you know eigenvalues of your transfer operator, and but then of course there are very some. I mean, for a non-perturbed case, so there are still some special features, like I told you. Yeah.
And the decay rates which you get in the classical limit are very interesting. Well, there are no interpretations, you're saying, because of the, I don't know, is there any interpretation of these? I mean, I would imagine that there would be some kind of generalization of the polyquadruple resonances, but after all, it's just decay of correlations, right? I mean, so
Yeah.
Yeah.
I don't know what. Okay, so I don't know what how to comment about this. So one thing which was very surprising for me is that you can actually, so it's in a sense it's simpler than single particle cat.
Okay.
Yeah.
Yeah, that's surprising.
That's kind of strange. Yeah. So especially if you think about symbolic dynamics, so because symbolic dynamics, it's maybe on the for a single cat, so you can also build up the same linear symbolic dynamics, and it's kind of you don't see simplifications on the level of many body systems. So it's more it has very similar features, but not something not. So you cannot think about these models as something trivial. Yeah. So it's by no means.
Yeah.
But somehow for a correlator, so you get very simple. Yeah.
Thank you, Boris.
Yeah.
Other questions? If not, let's thank Professor Boris for a very nice talk. Thank you, Boris. So we are going to end this session here. I would like to thank all the speakers who made this fantastic session. Thank you so much. We will reconvene at 6:30, where the first talk is our own Suhail. So please do